Hi everyone, and welcome to the fourth of 5 videos going through some past exam questions on buffer solutions. Just one question I'm going to do in this video. It's a bit of a long one, and they've given us a story to read here. We're going to have to read through all of this, unfortunately. Right, what's it saying? The magic tang in many sweets. Where they get these questions from, I have no idea. But let's just go with it. So tangy sweets comes from acid buffers. Okay, fine. The sweet manufacturers doing some tasting tests, and they identified the acid taste that gives the magic tang. Fine. They were convinced the magic tang would give them a competitive edge. This is riveting. Right, we're trying to find out the chemicals. Fine, whatever. Right, a pH of 3.55 is what we're looking for. Right, that's actually relevant. So we're trying to get a buffer at this pH. The chemist decided to use one of the acids in this table and a salt of the acid. Okay. Deduce the chemicals required to prepare this buffer. Okay. Right. So we've got to make a decision of one of this lot of which is going to be the best one to use to make this buffer solution. Okay. And so this is just worth 1 mark. We just need to make a decision, pick one of these. But I want to talk you through kind of the theory behind where do we get this from. So if we take a look at Ka, all acids questions start with Ka. I'm just going to do a generic Ka here because we don't know which one we're talking about. But the concept with the buffer solution then is that it should be able to minimize pH changes when we add acid and also when we add alkali. Okay, and to make a buffer solution, we need a mixture of a weak acid and its conjugate base. Now, for it to be able to respond to both acid and alkali, we need to have both of these things. And it would be best if their two concentrations were equal, because then it would be equally good at reacting with acid and reacting with alkali. Yeah, if I had like twice as much concentration of the weak acid, then that buffer will be really good if I add alkali to it, but it won't be as good if I add acid to it. Okay, we want these two to be equal, and then it's equally well prepared for either scenario. Okay. Well, if these two concentrations are equal, then they cancel out of this expression, right? And we're left with Ka is equal to H+. So that is the situation when a buffer solution is most effective, when these are equal. So a buffer solution will be most effective when its Ka is equal to the H+ concentration. Now, that's not really very useful. We can change this relationship into, if we take a negative log here and we take a negative log here, we can change this into saying the pKa is equal to the pH. And this is where it gets useful. So now we can say, for our buffer solution to be useful, we want this situation. So we actually want this situation. So if we know that our buffer solution, we want it to be pH 3.55, what we want is an acid whose pKa is 3.55. Okay, and that's how we're going to decide which of these we should use. We just need to pick the closest one. So we're going to be looking at this one here. So it's the lactic acid that we want. Okay. So that's how we're going to get the first mark. Okay, the page here is just literally a page of text, page of lines for you to write on. So to do this first bullet point, we want to make the buffer solution from the lactic acid was the one. And it did say deduce the chemicals. So we can't just say lactic acid because they said they're going to use one of the acids and a salt of the acid. Okay, so we need to say make the buffer solution from lactic acid and a salt of lactic acid. So, I don't know, sodium lactate, let's say, or potassium lactate, or, you know, whichever is your favorite lactate. I don't mind. Okay, so that has done this first bullet point. And that's all we need to say. We don't actually need to explain any of this business. We're just writing. It just says deduce the chemicals. It doesn't say explain why, blah, blah, blah. Okay. So we don't actually need to get into any of this. We then need to calculate the relative concentrations of the acid and its salt needed to make this buffer. Now, the key word here is relative. Why is that there? It's not just saying calculate the concentrations. Okay, they haven't given us they haven't given us very much information. We don't have enough information to actually be able to calculate the concentrations. But we can calculate the relative concentrations. By that, we just mean compared to each other. Okay, so we're saying when I'm making this buffer solution up, do I want equal concentrations of the two things, or do I want one to be twice as high as the other, or 3 times as high, or what? So this is actually the same type of question as we saw in the previous video. If we're looking for the relative concentrations, how do they compare to each other? We're working out the ratio. Okay, so it's like the question in the previous video with the carbonic acid buffer. So again, I'm going to write out Ka here. I can't emphasize this enough, that you just do Ka the whole time. But this time we're going to do it. We know now which acid we're using, right? So let's write it out properly with the lactic acid. So let's use the actual formula of lactic acid here. So what have we got? CH3, CHOH, COO minus. So we're doing this. And if we want to know the relative concentrations of these two things, we want this ratio. So we're going to rearrange this again. We're just going to get rid of the H plus by shifting it over there. So we're going to have Ka over H plus. And if we can calculate that, that's going to give us the ratio between these two, which is what we want. Yeah, if this comes out as a 2-to-1 ratio, that's we're saying, right, relative concentrations are, that one needs to be twice as high as the other one. So this is what we want to calculate. So we can do this then. So we need to know the Ka. We don't know the Ka. We do know the pKa is 3.86. So the Ka then is going to be 10 to the minus 3.86. Okay, remember pKa is the negative log of Ka. So to get Ka, we do 10 to the minus pKa. And what's the H plus concentration? Well, again, we don't know that, but we do know that we want to make a buffer with a pH of 3.55. So if that's what we want the pH to be, the H plus concentration will be 10 to the minus 3.55. Okay. So let's calculate that. So we're doing 10 to the minus 3.86 divided by 10 to the minus 3.55. And we get 0.48998 or something. So it's very close to being 0.5. I think we can get away with this. I know in the previous video it was 6.6 and I said just leave it as that. You could just leave it as this, they're not going to mark you down for it, but I think we can say, look, that's basically 0.5, right? So what that's telling us then is this divided by that is 0.5. So we've got a 1-to-2 ratio. Okay. So what we're saying is that the concentration of the acid should be twice as high as the concentration of the salt. Okay. So we can just write this. So the concentration of the acid is going to be 2 times the concentration of this one. Okay. Because 0.5 is 1 over 2, right? So this is the 2 and that's the 1. Okay, so let's go back to the question then. We've done this, calculate the relative concentrations. So now we just got this bullet point here where it says, comment on the validity of the prediction that the pH of the sweet would give it the magic tang. Now this is just an absolutely stupid question in my opinion. All they're saying is, look, the scientists have said that the magic tang, whatever that means, is basically a function of the fact that you've got it at the right pH. If you get anything at this pH, that's what gives you this magic tang. Is that a valid prediction? Well, who knows? I mean, what does that even mean? Basically, we don't know. The magic tang, whatever it is, could be coming from or any number of things, right? It's not necessarily just because it's at that pH. It could be due to any number of whatever chemicals you've got in this suite, right? And that's all it wants you to say. It's just a bit of a pointless 1 mark question. And I'm literally reading the mark scheme in front of me, and it just says, the magic tang could come from any of the other chemicals in the suite. And that's what they want you to write for a mark. So you're like, really? But if that's what they want. To me, this seems like, oops, we've made an exam paper that's 1 mark short. How can we think up another 1 mark to ask for? So magic tang could come from any ingredients in the suite. It's not necessarily from the pH. Well, it's not necessarily due to the pH, let's say. I mean, that's just daft question in my opinion, but there you go. So the main thing I want you to take away from this question is this part of it. Is if you ever see a question like that, because it's worded kind of strangely. So if you ever see this relative concentrations, I want that to sort of trigger in your head, go, I know what this is. This is that ratio question again, where we just rearrange our Ka to get this ratio.